Right. So today what we will be doing is going over a mistake I made in the last video. And I promise this will be the last video on the asteroid curve. Um, so when I was going through my notes, I saw that I made a blunder and I would like to see how we can correct it. Now, if you remember, and also by the way, if you have not seen the video, you should see it because I'll not be going over the entire solution. I'll just be correcting that tiny bit of the mistake that I made. Um, For those of you who saw the video, might remember that I derived the derivative of the line or the implicit function and set that to zero. And how the fact that the derivative with respect to c is zero is correct. So I wrote that tau f by tau c is equal to zero. And the thing is that this is correct. This is true. But how I got here is very, very wrong. So I'll start by defining the line again. And how we develop an implicit function out of this, right? This is how we defined our implicit function. And now I said that if we derive the derivative of this function with respect to c, we should get a zero, which is true. The argument is that if we change c little by little, the variation is such that the lines should be similar. Now, where I went wrong, I'll make it very clear. I stated that as epsilon tends to zero, this is wrong. So what I stated was that if we make a small change in C and we take the difference of these lines or these implicit functions, the functions should be zero. But this is not necessarily true. I made a wrong assumption here that x and y are stationary. So if x and y do not change, this statement holds true. But I forgot that x and y are also a function of C. We can see this visually. Now, if I map a point xy, x naught, y naught, if I make a variation in C, this point also transforms along the way. And this is something that I did not model. Hence, x and y being same is not true. So that is where this goes wrong. So changing C means changing x and y. Um, so the correct way to do this would be, right way to do this. So one of the critical errors that we made was defining the domain in C. That means, but as we saw that x and y also change with C, so the domain expands. Let's define a domain gamma, which is of C, which is x of C, y of C, C. Now this is our current new domain. So as C changes, so does x and so do y, so does y. And how they change is not really necessary. And there's a very neat trick, which is quite fantastic with dealing with the solve a problem. Right? We have seen that the implicit function is constant. This function, and I'll just draw a box around this. This function is constant. So for all values of C, this function will always be zero. That is how we have defined the line, right? So if the function is constant, the derivative of the function shall also remain constant with respect to that variable. So we say the total derivative of the function is zero. So instead of the partial derivative with respect to C being zero, which will be true, we'll come to that, the total derivative is true as well. This is where I made that critical error. Now what we can do is that because f is a function of gamma, I can rewrite this as gamma of C equals zero. Now, if we open up this function, we can actually write this as a gradient of f and the derivative of gamma, right? So this would imply that the gradient of f dotted with the derivative of gamma is equal to zero. And this, of course, is following simple calculus. Now, if we open this up, two vectors dot to be 0, we can make the fair assumption that both of these vectors are normal to each other, perpendicular to each other. So basically, a dot product of perpendicular vectors is 0. And we can also observe that dc by dc extends to 1. The derivative of c with respect to c is 1. And now what I'll do is I'll try to split this in two parts, taking x and y as one part and the dou f by dou c as one part. And you can pause and verify that this is true. This is basically opening up the vector. We can also open up the first part, which will be dou f by dou x into dx by dc plus dou f by dou y into dy by dc plus dou f by dou c to be 0. But why I did it this way is to show why this is true. What we want is our dou f by dou c term to be equal to 0. How do we achieve that? That'll only be true if this whole term on our left is also 0. Now, why would that be 0? Is a pertinent question. Now, what you need to understand from the geometric meaning of this entire problem is that we have this graph where we have this asteroid curve, and we have a line that is tangent to this curve. Now, this is our function f, and this is our tangent, independent of c. Independent of c, for all c, the derivative of x and the derivative of y form the tangent of f. So the gradient of f is in this direction and the derivative in this direction. So they are perpendicular to each other. And because they're perpendicular to each other, their dot product also turns out to be 0. Thus, dou f by dou c by itself is 0. This was just to show where I went wrong. Of course, the result came out to the same, which was not good because that basically confirmed my bias and showed I was not able to correct myself. But I hope I was able to convince why dou f by dou c is still 0. And of course, from here you can carry on the derivation as I did in the last video. But it is pertinent to understand why this particular part is also 0, because this is only in the spatial dimensions x and y. The other added parameter independent of c, for all c, the derivative is tangent to the function, because the function, the separate lines, form the envelope of the asteroid curve. So I hope I was able to convince you that this is the case, and hopefully I do not make this mistake again, such mistakes again. Thank you for watching. Bye.